Good day to Dr. CHEE and whoever watching this video. My name is HAZIQ bin Abdul Hadi with metric number BR23110190. I'm honored to stand before you as the representative of our group, Group 20, to present our bug population assignment Part A for the subject RC20903 plant breeding. First of all, this is my group members from Group 20. The definition for the bug population is the term that refers to something that exists in large quantities, often without individual packaging or separation. Meanwhile, population is defined as a group of individuals of the same species inhabiting a specific area and interacting with one another. When combined, bug population refers to a plant breeding technique used to develop new crop varieties, particularly in self-pollinating species. This method involves growing large populations of segregating generation derived from a cross between two or more parent lines, with minimal selection pressure applied during early generations. In brackets Sotosanti 2023. Next, I will talk about context. In the bug population method, F2 and subsequent generations are harvested in bulk to grow the next generation. This process is typically repeated for several generations, usually until F6 or F7, allowing natural selection to act on the population. The key principle behind this method is to maintain a large, diverse gene pool throughout the breeding process, which allow for the gradual accumulation of desirable gene combinations while eliminating unfavorable ones through natural selection. In brackets SING ETAL 2023.
Next, I am Boyd Isaac JAILIS with number metric BR23110191. In this slide, figure 1 shows the generalized steps in breeding by bug selection. The bug population breeding method is a systematic approach specifically designed to develop new varieties of self-pollinated crops, with soybean being a primary focus. This method emphasizes advancing generations as mixed populations, allowing both natural and artificial selection to shape the genetic landscape of time. The entire process typically spans several years, starting from the initial parental crosses and culminating in the release of a superior soybean cultivar. In the first year, two parent soybean plants, each exhibiting desirable traits such as high yield or disease resistance, are crossed to produce the F1 generation. The resulting F1 seeds, usually numbering between 50 to 100 plants, are then grown and harvested in bulk. This step is crucial for establishing genetic variability within the population. The harvested F1 seeds are sown in the second year to produce the F2 generation. Approximately 2,000 to 3,000 soybean plants are cultivated at a commercial seed rate under field conditions. During this stage, natural selection plays a vital role as it acts on the population, effectively eliminating weaker or less adapted genotypes. Seeds from the entire bug population are then harvested to advance to subsequent generations. From year 3 to year 4, bug planting continues for the F3 and F4 generations, maintaining a population size of around 2,000 to 3,000 plants per generation. Throughout this period, natural selection remains significant, while artificial selection may also be introduced to enhance traits such as disease resistance and stress tolerance. Each year, seeds are harvested from the entire bug population, facilitating gradual increases in homozygosity. In year 6, the F5 generation undergoes space planting, where approximately 3,000 to 5,000 individual soybean plants are grown in rows. At this stage, deliberate selection begins to focus on superior individual plants that exhibit desirable traits like high yield potential and pest resistance. Seeds from the selected plants are harvested separately for further evaluation. During year 7, individual plant progenies from the F6 generation are grown in rows for refinement. Around 300 to 500 progenies are evaluated for uniformity and performance within each line. Inferior progenies are systematically eliminated, and seeds from the best performing lines are harvested individually for further testing. In year 8, preliminary trials are conducted on approximately 30 to 50 selected lines to assess their performance under controlled conditions. The most promising lines based on yield potential and adaptability are advanced for further testing. From year 9 to year 11, advanced yield trials take place across multiple environments to evaluate performance stability and adaptability of around 10 lines. Ultimately, one superior line is selected for release as a new soybean variety. Overall, this breeding method effectively combines natural and artificial selection over successive generations while minimizing labor during early stages. It ensures that only the most desirable traits are retained, leading to the development of high-performing soybean cultivars that meet agricultural demands.
I am Olivia Honesta SINTAR with metric number BR231101 at 6. The purpose of bug population. Firstly, natural selection. This method ensures that only plants best adapted to the growing environment survive and reproduce. Second, advancing generation. This method facilitates the advancement of segregating generation to achieve homozygosity while maintaining genetic diversity in the population. Third, cost-effective breeding, designed to handle large population inexpensively, making it suitable for resource-constrained breeding programs. Fourth, trait selection. Artificial selection can be applied in specific environments to select for desirable traits such as disease resistance or drought tolerance. Next, significance of bug population. Firstly, adaptation to environment. Through natural selection during bug population method, plants may adapt to local environmental conditions, enhancing their resilience and performance in real-world setting. Second, simplify management. This method simplifies the handling of large population without requiring detailed record keeping of individual plants, making it practical for crops grown at high densities. Lastly, preservation of genetic diversity. By advancing population without early selection pressure, this method maintains genetic variability, which is crucial for long-term crop improvement.
I am Veronica DAIRIS with matrix number BR23160195. For the next part is benefits of bulk population, which is the first one is low cost and technical simplicity. The bulk population method requires fewer resources and less technical expertise compared to other breeding methods like pedigree breeding. For the second one, efficiency in large population, it enables breeders to manage large numbers of individuals collectively, reducing labor and logistical challenges. For the third one, flexibility in selection, natural selection operates during the bulk phase, but breeders can also apply artificial selection at specific stage to target traits of interest. For the next one, adaptability across crops. This method is effective for small grain crops such as wheat, barley, and oats, where the planting densities are high and individual plant tracking is impractical. For the last one is rapid inbreeding. This method advances generation quickly toward homozygosity, often achieving this state within a few cycles under controlled conditions like greenhouse.
Hello, my name is JOAWENCY RINING, number matrix BR23160197. Application. Firstly, crop breeding programs. Widely used in breeding small grain crop where large population can be grown and handled efficiently. Second, stress selection environments. Blocks can be grown in environments designed to mimic specific stress to select plants naturally resistant to the stress. Third, genetic diversity maintenance. Ideal for preserving genetic diversity in early generation before intensive selection are applied in later stage. Lastly, marker assist selection integration. Modified version of the bulk method which use molecular marker to select desirable traits during early generation while maintaining the benefits of bulk handling.